Okay, great. So thank you, everyone. I'm here to talk on behalf of NOAA and myself about the Lunar Reconnaissance Orbiter um, and the data, especially that we can still acquire in our Artemis region, which we're defining as within 6 degrees of the pole, and talk a little bit about that and some of the uses of that data and where we're going from there. There we go. I thought we'd start with just some fun facts about LRO. So LRO is now in its fifth extended mission. So that began in September of 2022 and will continue on through September of 2025. LRO data has been featured in over 1,020 peer-reviewed publications, and LRO is coordinated with numerous NASA missions as well as international missions. It was the first to observe a new impact on an airless body, and has made, of course, numerous scientific discoveries and investigations, just to name a few on listed here on new forms of lunar volcanism, unusual regolith around young craters, and especially characterizing that polar environment. Um, Importantly, LRO has generated the largest volume of data of any NASA Planetary Science Division mission. And actually, it represents more than 65% of the total data volume of the PDS. So by the end of our ESM5, it will bring the cumulative life of LRO to over 16 years. So that will ultimately create a singularly unique volume of data for planetary science. And in particular, this extended mission will feature multiple missions to the lunar surface, not only Artemis, which we're of course talking about now, but also CLIPS, which has missions planned or deliveries planned to 11 unique locations on the surface of the moon, several of those in our Artemis zone. So LRO is poised to support and enhance those missions with the data that I described here in the South Polar region, as well as many other data and observations, very similar to what we've been doing all along in the non-polar regions. So I just wanted to talk for a minute about LRO's orbit. Many of you are familiar with the changes to the orbit over time, but just as a little summary here, LRO's orbit will be nearly circular for the first time since 2011 during this extended mission. We have some plots here showing changes in the altitude over time, and in particular, LRO will be closer to the North Pole than it has been in a decade. So what does this mean for us? So LRO also, since arriving at the moon in 2009, that orbital inclination, which we show on this plot over here on the left, has been slowly drifting away from the poles at a rate of about 0.5 degrees per year. So the result of this drift is that the latitude at which we get our densest number of passes, which initially was 90 degrees north and south latitude, that's been slowly shifting away from the poles. And we like to call that for fun the ring of fire. And to demonstrate that ring of fire over here, this is a figure showing this density of orbital passes. And in red is the densest area of orbital passes. This is throughout our ESM5. And so that's our ring of fire right here. And this area in the middle are areas that are not going to be underneath the orbital pass of LRO during ESM5 moving forward, from now moving forward. But of course, are areas that were covered in prior mission phases. And LRO has a wealth of data and data products with coverage of those areas, including the Artemis zone, of course, that are already publicly available and have been instrumental already in assisting with CLIPS landing site efforts, and already as NOAA was mentioning, informing our efforts with Artemis landing site selection thus far. So what does this mean? So the LRO orbit, will be over illuminated terrain within the Artemis zone on most orbits during ESM5. So I'll bring your attention back to this plot on the left here, and you can see how the inclination is changing, but through 2026, we are still have orbits that are over at least the northernmost parts of the Artemis zone through that 2026. additionally, that current orbit enables studies focusing on these other areas of dense coverage. To address questions require a high cadence or a high temporal resolution of observations, in particular volatile studies. And so in those northern edges of that Artemis region, we have some new opportunities to investigate things with a density and high temporal cadence of observations we haven't had before. And for these locations in this, dare we call it a bald spot, further south, LRO can still acquire oblique observations and limb views. This is via a slew, anywhere up to and including the South Pole. And that's from many of the orbits and throughout all of ESM5, so through 2025. So let's talk a little bit more about some of those observations. I'd like to start with LROC. So the LROC camera, as I mentioned just now, it can acquire those oblique images anywhere in that region, including all the way to the South Pole throughout 2025. And this imaging is especially favorable during the lighting of summer. And of course, this offers the potential for contemporaneous observations with Artemis 3 surface operations, which is really important to just get an orbital view of operations, and if we can resolve things at the landing site, localization, and many other benefits, of course. So what does this mean, though? What does that look like? So I gave an example here. When LRO orbit is at an 85-degree inclination, let's use for an example, the distance to the South Pole from our 100-kilometer altitude is roughly 185 kilometers. So that will give our NAC images a pixel scale of roughly 5 meters at a slew angle of just a little over 60 degrees. So not the LROC NAC resolution that we know and love, but we can still get some pretty nice pictures obliquely. And just gave an example here of a connecting ridge, which is just a few degrees from the South Pole. So let's talk a little, whoops, I went too ahead. I also wanted to talk about LROC and landing site characterization. So LROC NAC DTMs are available for portions of 2 of the sites. And the LROC team is continuing to investigate production of DTMs covering additional regions in Artemis 3 sites. Very importantly, the LROC team is also working on 1 meter per pixel LROC NAC controlled mosaics of all 13 of the candidate landing sites. And these are offering the highest quality controlled image products that are currently available of these landing sites. And of course, will be important for characterizing the geological context. And of course, for surface operations planning and hazard assessment. These will be available as RDR products that can be downloaded through PDS and also QuickMap and LunaSurf. And I'm going to save the details of that for my colleagues on LROC. I listed the abstract down here, and they will be giving a talk later in this session. So let's talk about MiniRF. MiniRF has a bistatic data campaign in the South Polar region with X-band observations of Earth-facing portions of the South Polar region. These can be processed with a resolution of roughly 100 meters in range and azimuth. They can also get some coverage of PSRs afforded by lunar libration. And my colleagues with MiniRF are going to talk a little bit more about these next bullet points in their talk, but wanted to call it out here that their data can be very important for landing site characterization, especially when combined with the DF-SAR instrument, which is currently is also a monostatic system with L and S band observations and is currently acquiring data. Combining those 2 data sets together can enable characterization of the landing sites for both science and engineering applications, and as well as an identification of potential hazards such as roughness of the near surface layer, providing insights into subsurface structure, and also constraining bulk density and composition. LOLA can also document illumination and visibility conditions during at our Artemis landing sites during mission timelines. They will also be attempting pre and post landing passive radiometry. So that's using the sun as the light source rather than the laser targeted at those landing sites. And this will be to look for reflectance changes in the blast zone. Also, they will attempt to range to lunar retroreflector arrays or LRAs on south polar landers. And that's, so far we're having LRAs on some form of retroreflector on all of the CLIPS landers, including those that are going to the south polar regions, and of course any LRAs that are on Artemis assets. And so this will be challenging in terms of position and pointing predictions, of course, and the success will depend on where the pointing of the LRA and the landing site location, but will be really important for localization and cross-validation of LROC obtained coordinates. So I wanted to talk, I wanted to talk also about a little bit more about the LOLA DTMs, of 5 meter per pixel DTMs, which have already been mentioned in this workshop. Of course, these exist for all of the 13 landing site candidate regions, but are also being worked for additional areas of interest, and are just, important for their improved horizontal and vertical uncertainty, fewer artifacts, their geodetic control, and or what can be used for lunar data sets to locate their data within roughly 10 meters horizontally and 1 meter vertically. And these DTMs can be used and are being used to derive additional products to better understand surface height, slope, roughness, reflectance, and very importantly, solar illumination and earth illumination. And my colleagues with LOLA will also be talking more about this later in this session. So Diviner can also acquire oblique observations of high priority targets. This will provide additional insights on the range of temperatures, of course, at sub-Diviner spatial scales, but this particularly viable roughly 2 degrees of latitude oblique to the LRO orbit track, and also offers the potential for contemporaneous observations with Artemis 3 surface operations, which is really exciting. Diviner will also be leveraging that slow rotation of LRO's orbit tracks near that ring of fire to obtain high temporal resolution coverage of different areas of interest, and use slewing off nadir to take repeat observations on several different orbits. And for landing site characterization, Diviner, of course, provides us with our understanding of temperatures, and along with the illumination modeling, provide valuable information about the expected thermal conditions that will be at each of our candidate Artemis 3 landing sites. They have a capability to at least predict temperatures versus time for a given location. And using the best available topography, the Diviner team can use this, can and will be using this existing data to create higher spatial resolution models of polar ice stability in these sites of interest. And again, my colleagues will be talking about this a little bit more in a later talk in this session, but also see their abstract. LAMP can acquire those oblique observations simultaneously with LROC slews, again, adding to landing site characterization, and also the potential for those contemporaneous observations with Artemis 3 surface operations. And additionally, very important, will be taking advantage of that high temporal resolution observations in that ring of fire area to further characterize volatile transport. And this brings us to Crater. Crater will continue with its continuous observations that will be used to predict the strength of the solar cycle during which Artemis will operate. And by monitoring crater measurements through the rising part of this cycle, the team can more accurately predict the galactic cosmic ray environment anticipated during Artemis missions. And as my last slide here, I wanted to just point out an investigation by Crater, which they're going to provide a better predictive capability for radiation exposure at the lunar surface to aid in mission planning and operational planning and such. So what they will be doing is taking coincident orbital radiation measurements with deployed surface experiments to support predictions of the radiation exposure at the surface. And so I just listed a couple of those surface assets that are being anticipated in the near future, including, for example, LETS, which is scheduled to fly on an upcoming delivery of Task Order 2 Astrobotic, the Peregrine lander mission, which is due to launch this year. Rad PC, which is on task order 19D going to Mare Crisium, and some others there, including NSS on Viper going to the South Polar region. So they will use these coincident measurements of radiation to generate radiation exposure maps of landing sites in regions of interest, and using also those crater observations in conjunction with LOLA and LROCA DTMs. So this will enable enhanced predictive capabilities related to radiation exposure on the surface, and also help to identify better shielded locations for astronauts or surface assets to plan safer operations. And additionally, will provide more insight into variations in space weathering and volatile sequestration that might be related to that radiation exposure. So that's most of what I wanted to talk about today, but I didn't really get into the existing LRO data. So I'll just invite you to please visit QuickMap to explore the LRO data that's there and the data products, especially with their coverage of the South Pole and the Artemis 3 candidate landing regions. There's an incredible wealth of data, and I also invite you to explore some new QuickMap capabilities that can assist with looking at this data in different ways and with landing site characterization, and put yourself right down on the surface and influence the time of day and see where the sun will be and the earth will be, and play around with this manipulation. It's really fabulous. And if you have any questions about data and things we can potentially do with LRO data and new data products, please reach out to myself or Noah. Thank you.
Yeah, thanks, Maria. There's a lot of really great information in there.